Okay, let me first introduce Professor David Pan a little bit. So Professor David Pan right now is Silicon Laboratories Indoors Chair Professor at Chandra Department of ECE, from the University of Texas at Austin. His research interests include electrical design automation, synergistic AI and IC co-operations, design for manufacturing and hardware security, and design CAD and analog and mixed signal and emerging technologies. And Dr. Pan has published a lot of journal and conference papers, and have 8 US patents, and he has also been served as a committee, committees in let's say DAC, ICCAD, and a lot of hardware top conferences. Yeah, so and Dr. Pan also has got a lot of awards like NSF Korea Award, IBM Faculty Award, and some awards from the CAD context. Yeah, so let's so we are very happy to have Professor David Pan here to give us this seminar. Yeah, so David Pan, you can Dr. Pan, you can take over. Yeah.
Okay, can you see my screen?
Yes.
Okay, all right. So thank you very much, Pan, for your kind introduction, and it's my great pleasure to be here and share with you some of our recent work to close the virtuous cycle of AI for IC and IC for AI. So as we all know, right, AI has received a lot of booming recently, and the ABCs behind AI really are A and B and C. A stands for algorithms. Many new algorithms have been published, from CNN to RN to GAN to all the transformers and so on and so forth, right? And then there are a lot of data nowadays, right? There's our big data, and meanwhile, the C here is really chips, right? The underlying all this algorithm to run on this huge data, you need a huge computing powers, and thanks to all the CPU, GPU, application-specific ASICs, and so on and so forth, right? So now we can run really huge models. So, but designing those chips or IC integrated circuits is non-trivial. Especially nowadays, right? We are talking about nanometer dimension. So designing those is tremendously complicated. For example, this is a chip developed by NVIDIA a few years ago, actually. It's on TSMC's 12 nanometer and with 9 billion transistors. Nowadays, right, you probably reach 100 billion transistors or pretty soon trillion transistors. But it took 8,000 engineer years to design this big SoC chip. Usually you have to divide this large chip into many smaller partitions, and each partition maybe with 1 to 2 million cells. Even that, to close timing and power, performance, etc., for one partition could take days or even a week, right? That's why it takes so much time to close this big chip. And you probably also heard about Cerebras, which actually they are kind of pioneering in this so-called wafer scale chip. The entire wafer is a chip, right? So it's dedicated for AI applications, and they have already had a version 1 and now version 2 with trillion transistors. And well, most time when you talk to circuit designers, when you say, oh, we finished the design, they say, oh, we have a bunch of GDS2. They have a bunch of basically many layers. They have transistor layer, they have metal layer, vias, contacts, and so on and so forth, right? So those are a bunch of rectangular shapes. But when you send it to the fab to be fabricated, you have to use the lithography process. And those lithography process actually now, as you are pushing to the really advanced technology nodes, it could easily distort your original design intent. So you have to do very fancy so-called optical proximity correction or something like that, right? So to really make it to print as close to what you intend to print, right? So these are all not trivial. So that's why design and manufacturing is really complicated process. Here is just some overflow. As you can see, at the higher level, if you are a software guy, you may write some Python or C++, and then say, hey, let's try to synthesize it into some netlist, maybe RTL, right? register transfer level, and then you map them to logic gate like NAND, NOR, AND, OR, and the exclusive OR, etc. And then you will also use the standard cell library and use from the cells from the library. Then you can kind of do a technology mapping and map them, and then you have to ultimately place them into two-dimensional, like a chip area, such that you will, like you have to do placement and routing and so on. And also nowadays, when you are doing routing, you typically have many routing layers, maybe 10, 15 metals to finish all the routing. And then you have to generate the mask and do mask synthesis and verification. Then you fabricate, right? And then you package the chip, right? So even for physical design, which is one core step in the entire design flow, it has many sub-steps, such as floor planning, placement. Those floor planning are planning big blocks, right? But placement, you are talking about millions of, tens of millions of smaller cells. Then you have to generate clock, you have to do routing, and so on and so forth. And then even for mask synthesis, as I just showed you, right, you have to actually generate some lithography models, and then which help you to generate a mask optimization and all kinds of checking. So it's a very, very complicated process. And let's say, any of this process, you may see this is a one-dimensional linear, way, top-down, right? But any of this, you found some problems, you have to go back and then maybe iterate. Of course, if you are like already fabricated the chip and you have to go all the way back, that's a huge, like money, like a loss, right? So, but that's why it's very, very expensive to do all this, power performance area closure. And then you also worry about manufacturability and yield. And then there's also reliability issues and security, right? So, and then design cost, right? So design cost actually is a significant problem. And since we are at the university, we oftentimes talk about workforce development, right? So, and we don't really have so much engineers who really know what's going on here. And the design cost is actually, scale up, like also in an exponential manner as you go to the advanced technology nodes, right? So that's why, a few years ago, DARPA posted a grand challenge. And they also have a $1.5 billion ERI project, Electronics Resurgence Initiative. And under that, there's an Idea Push program, which basically is for Silicon Compiler 2.0. So I know that this audience is very interdisciplinary. If you are software engineers, you write some code, you would like to compile it, right? You want to see the result. Can we basically write some code and the higher level and even compile it to silicon, right? So of course it's non-trivial, and there's a lot of process need to be really redo, or need to be re-accelerated, or need to be redone, right? So, and in the entire process, of course, hopefully the AI can help, right? AI, machine learning, they can do prediction, and they can also do acceleration, and so on and so forth, right? So my talk actually today will be based on two main things to address this AI and IC interactions. So basically, on one hand, when I say AI for IC, essentially, how do we leverage the recent AI techniques to enable agile and very intelligent IC designs, so that we can get equivalent scaling of Moore's law? Right? Everyone knows about Moore's law, but Moore's law depends on the, in the past has been heavily depends on the CMOS scaling. But the CMOS transistor now is already like very close to the physical limit, right? 3 nanometer, or or sub-nanometer. I mean, how much further can you go, right? So if you're in physics, that this is actually is pretty hard. So, but in terms of the design, actually, there's a lot of the suboptimality actually out there. So if we can kind of unleash all the design potentials, as you can see, I showed in the previous flow chart, right? There are so many abstraction levels, and so although they actually make your design simpler, but they, on the other hand, they make your design maybe suboptimal, right? So how we can then, democratizing the IC design and the EDA, and so that's actually one of the key things here. Another, of course, we always want to build better ICs, better AI accelerators. and so that your AI can be run in a more efficient and also effective way, right? So think about it, right? So when we talk about Moore's law, people have been familiar with Moore's law, right? This is, your number of transistors will double every 2 years or so, right? 18 months. So it has been true for 50+ years. That's really amazing, right? But in terms of the software side, AI also has seen a lot of a boom in terms of, for example, the number of machine learning papers, right? But I mean, in that sense, if we have like AI algorithms and the hardwares work together, hopefully we can close these virtuous cycles and to keep on pushing whatever the Moore's law or Moore's times more, right? This kind of exponential growth. So in the next, I would say maybe 40 minutes or so, I will basically focus on 2 aspects and show you some case studies of this AI for IC design and IC for AI. Right? So most of my time will be on AI for IC design because the main research in my group is more on the EDA side, but I also design IC chips, in particular photonic IC chips to do machine learning accelerators, and which also has some, co-design issues there for hardware, software co-design. So the first case study that I like to show is for the placement. So this is a paper that we published 3 years ago at DAC, which is a flagship conference in EDA, design automation. And we also got the best paper from IEEE transaction on CAD last year. So DREAMPlace stands for Deep Learning Toolkit-enabled GPU acceleration for modern VLSI placement. We have also made the source code available, and you can download it, and it's already been widely used by industry, including Google, NVIDIA, Intel, etc., and also academia. So it has hundreds. I think probably it was, I took this snapshot a couple of weeks ago, so probably there are more folks downloading or trying to focus. Right? All right, so what is placement problem, right? Placement is actually a very fundamental problem. In VLSI design. So basically, when you have a chip, right, you have a bunch of big macros, these big blocks, right? You also, you may have hundreds of these blocks, but meanwhile, for this red little dust, these are standard cells, and but compared with these are smaller, but you have tens of millions of them, or even more, right? If you have billion transistors, you will have maybe hundreds of millions of these, right? So it's a very, very large problem size, and your task is to place those blocks and cells on this 2-dimensional kind of area, maybe let's say 1 centimeter by 1 centimeter area for a big chip, right? So your job is like, hey, I do not allow any overlap between these cells and blocks, and I want to minimize the total wire length or minimize some timing or power or whatever metrics, right? So this problem is a very classical NP-hard problem. It's a very hard problem because of the non-overlapping constraint. And the placement is also plays a central role in IC design closure because it is in the middle of the entire design flow, right? As I shown you before, right? So physical design is somewhere in the middle, right? And then placement also is, is very important because without placement, you don't know how long the wire is, right? Because as you can see, right, between this, there are connections between the cells, and without placement, you don't know how long your connections, the wire is, and the wire actually now dominates the overall circuit performance, power, and so on and so forth, right? So, I mean, I'm not going into the details of give you a history of the placement, but placement has been studied for 50+ years. It's a very well-studied topics. And but still, there is actually a lot of still a very active research topic. It's just this problem is just so hard, and people have developed early on like partitioning-based algorithms or simulated annealing or some other analytical solvers, right? But the current state of the art is a nonlinear placement algorithm, which based on something like this formulation. So essentially, you want to minimize total wire length, but subject to certain density constraint at any area, you want your density to be smaller than certain target, right? Because otherwise, like I showed you before, if everybody is just on top of each other, that's not interesting. Like, when you initially run the placement engine, right, you need to spread them. So then you want to minimize the so-called total summation of total wire lengths. But you can also put the weight in terms of wire lengths, such that, if some wire length is more critical than others, you give it higher weights. And to solve this constraint optimization, we can also, transform it into an unconstrained optimization with this lambda Lagrangian multipliers, which you can adjust, right? And then you can think about, wow, how do I solve it, right? So think about it, right? The problem size is very big. You are talking about millions or tens of millions of standard cells. So it's a huge problem. And you want to have very fast runtime. So to get a good, state-of-the-art placement, engine, actually is non-trivial. Typically in the past, it easily take a year for people to develop it. So of course, what is your dream placement engine, right? So I always challenge my student, right? So you have to think big, you have to dream big. So we definitely want to have the best quality in terms of wire length, congestion, timing, power, and so on and so forth. You also want it to be really fast because the placement is at the center stage of the entire design flow. So, faster means that you can actually get better, turnaround time, and you can actually get better quality of results. And also you want it to be low development effort. So instead of maybe spend a year, if I can just develop a new placer within a month, that would be nice, right? And also if I have new algorithms and new acceleration techniques, hopefully, I can also leverage that, right? So what is the DREAMPlace strategy, right? The DREAMPlace strategy is that actually we propose a novel analogy by casting the nonlinear placement optimization into a neural network training problem. So essentially, you will see soon, right? So we can then, once we've cast it into a neural network training problem, we can greatly leverage deep learning hardware and the software toolkits to develop a ultra fast, ultra high parallelisms, placement engine, which can get state-of-the-art result, but, it's like 30, 40 times faster than the previous state-of-the-art. So here, let me show you the analogy between neural network training and replacement. As we know, right, typically when you have a neural network training process, right, so you have your neural network and then there's a weight to be trained, right? So you have a bunch of data instance comes in with the label, right? And then for forward propagation, you can compute the error function, with respect to your label. But then you can compute the backward propagation with respect to the error function, and then you can kind of go back and forth, and then ultimately you train your weight such that later on, if you have any picture, you just pass it, and then with your trained weight, you can do an inference and then quickly tell it whether it's a dog or cat and so on and so forth, right? And also, instead of just the error function, to avoid overfitting, you can also add some regularization functions, right, into your objective function or error function. So if you now look at your placement problem, it's actually surprisingly the same, looks the same, similar. Basically, I'm trying to minimize the wire length, and meanwhile, I want to kind of make sure the density is more or less even. So then, you can now mimic and cast it in like, oh, what's your data instance? Your data instance is your net list, right? And then you want to minimize wire length. So that's why you give it the target of 0. And then the error function will be the wire length. And then what is your weight? The weight essentially is the XY location of your cells that you need to place them, right? So then you have forward and backward propagation. Then you can actually do the, if you do it well, then you can get a very good placement engine, right? However, of course, I skipped all the details and the things that, of course, how do you compute wire length? How do you do, density computation very efficiently? So, but to give you a key idea, right? So then, by developing, to develop our DREAMPlace, now, we can actually greatly leverage those very highly mature and optimized nonlinear optimization, engines and automatic gradient computing, convolution, or those stuff from CUDA library or from Python library, right? Then what we need is to add a placement API plus, of course, wireless and density computation, right? Because of the time limit, I won't be able to show the details, but essentially, we also have developed different ways how to do it highly optimized. And then we also try to match another well-known like nonlinear optimizer, Nestor's method, which is widely used for previous state-of-the-art placement engines. And then we can actually, build a new placer, what we call DREAMPlace. So to show, by the way, as a DREAMPlace, most intellectual merit is on the global placement. That is a nonlinear placement. And after that, you will still need to do legalization, need to do some detailed placement, right? But those are pretty standard stuff. So then we compare DREAMPlace versus the previous state-of-the-art, placer, replace from UCSD. And we try to match the parameter, etc., such that they have the same quality of results. And however, we found that with DREAMPlace, we can have 30 or 43x speed up. So for DREAMPlace, essentially, we only use one GPU to actually do this kind of mimic the training process to solve the placement problem. And for this, previously, they're using many core, like 24 core CPUs, right? And so that actually, to the first time, we can finish this 10 million cells in a minute, right, instead of several hours, right? So as you can see, right, because placement problem is such a fundamental problem, so it's actually very important and to have really fast runtime. So remember, when we have DREAMPlace at the beginning, we have a bunch of dreams. We want to have the best quality of results. We want it to be really fast. We wanted to have a, by the way, my student it took him like 2 months, 1 to 2 months to finish developing this. Compared previously, when we talk with replace developers, right, it easily took them a year, right? So then also, we want the algorithm to be very extensible, right? So actually, with all this, the dreams come true, but we can also dream bigger. So as you can see, right? So in the machine learning community, right, there are many solvers. You can try different solvers, and also you can consider different objective functions. Because in the DREAMPlace original version, we only consider wire length, but you do have routability, timing, or other constraints, and no problem, right? We can actually consider those constraints. And then for machine learning community, people have always been doing the multi-GPU, distributed computing, mixed precision, etc. Right? So those techniques can also be used to help your this training process to converge faster and with less computing power, right? And we also have collaborated with Google Brain to extend this and work with reinforcement learning for macro placement. And we also extend our DREAMPlace to FPGA, to basically DREAMPlace FPGA. And anyway, so what I'm just trying to say is that DREAMPlace framework is very general and it can be used for other purpose. All right, so this is my first case study, and let me also move on to the second case study, which is for analog IC designs. Right? This is also part of the ERI program, and we have also made the MAGICAL open sourced 1.0. So the previous DREAMPlace mainly focused on digital IC, right? But analog IC is very important because they interface to the outside world. And however, analog IC layout and design are still mostly manual, and which is very tedious and error-prone. So the reason analog IC design is not as successful as that in digital IC is that, first of all, right, you are not talking about many millions of standard cells or transistors, right? Because if you are doing that kind of scale, no human even want to play with millions of things by hand, right? So there is no way. So analog designs, typically they have much less number of transistors, for example, hundreds or even sometimes less than 100. But those designs are very, very complicated in the sense that they have so many design constraints and they have to follow all kinds of symmetric, maybe common central, and all kinds of design constraints, right? So what we have done is that we leverage both human and machine intelligence. Then we actually developed a fully automated analog layout systems, MAGICAL. And we have published many papers on this. And so the key framework of Magical looks like this. Basically, you have a netlist inputs, right? And with certain PDK design rules. And the Magical will generate constraints, placement, and routing, and also device generation, which as input to the placement engines. So then with all this, the output is a GDS2, which is DRC and LVS clean. So in this process, of course, there are a lot of components in Magical. I won't have time to show all the details, but the key idea is like, we will use, analytical techniques, analytical placement, like, what I showed in DREAMPlace, but it's for analog designs. So you will have a bunch of constraints, for example, symmetrical constraints and pattern constraints, and so on and so forth, right? And meanwhile, with a router, and so we can actually, build a complete systems to do analog layout. So our framework can handle not only just the block level, block level synthesis. Let's say if you have a pretty complicated design, like analog digital converters, ADC, right? So typically it also has several components there, and and also then you have a top level circuit. So we can do block level synthesis, and then once we finish block level, we can then also do top level layout generation. So in that sense, we can do hierarchical layout synthesis. If you have very big design, you just decompose them into different hierarchical levels, and then you gradually move down to the lowest level, then you finish them first, and then you gradually build up the entire top level layout. So with that, actually, we even tap out pretty complicated ADC circuit, a third order high performance continuous time delta sigma modulator. And as you can see here, right, we have various support block, including 3 integrators and 2 like DACs and 1 comparator and some digital logics. So here is a kind of schematic, and this is a micrograph that are the tap out we have done. So it is actually tap out using TSMC 40 nanometer process technology. And actually, we have got state-of-the-art, performance compared with the original manual layout. So let me show you. So this is the original manual layout by a senior PhD student of my collaborator of this work, right? He's a hardcore analog circuit designer, and I'm of course a more design automation person, right? So without going into details, right? So as you can see, these are several columns, right? These are their comparison with some previous designs. And this is their manual design using this circuit architecture. So it's a pretty good performance. However, because at that time, right, the students have to lay out everything by hand. So it took the student like order of months to finish all this and the feedback and the simulation and so on and so forth, right? However, with our Magical, right, we can do this in minutes, right? And we can get some kind of, this is, by the way, the more like a flow planning top level, right? So we have a signal flow to guide our Magical, but within each of these small components, by the way, right, it's not really the same, right? So because, everything here is done automatically, including routing, but here everything is done by manual. So now if you look at the performance between this and this column, so they are actually pretty similar. So to a certain extent, some of this, our automatic layout even get slightly better, for example, SNDR, but slightly worse in SFDR. Right? But anyway, overall speaking, the figure of merit is very comparable or even better, right? So we also have extended Magical to handle even bigger systems like a SAR ADC. Which has more regular arrays, but plus at the top level you have bigger integrations. We will combine digital automatic placement routing plus Magical plus template-based generation plus all this Magical for the top level integration. And we also tap out 2 chips and verify at TSMC 40 nanometer. All right, so we also have extended the Magical to handle, FinFET technology. So the previous Magical, was tapped out using TSMC 40 nanometer, which is a bulk process. For the FinFET, usually it's much more complicated, and so we have collaborated with NVIDIA, and actually, so to extend the MAGICAL to handle what we call autocraft for FinFET process technologies. Again, it has, I won't go into details, but basically you have netlist, and I mean, to handle FinFET, you have to do some kind of abstraction with certain primitive mapping and some grid configurations. And then, we can, formulate the placement using some kind of SMT problem. It's kind of satisfiability modulation, modular, so essentially kind of like SAT solving problem, right? And then we also have some customer routing to solve this. Again, I won't go into details, but our collaboration with NVIDIA and also showed that very promising results even for 5nm FinFET process and some advanced designs. Right? All right, so now let me move on to the third case study for AI for IC design in terms of manufacturability, reliability, and security. I mean, I just quickly touch some of the work here, right? As I already shown before, right? So in the more advanced chip, right? What you see in the layout in your design is not necessarily what you will see in your, final chip, fabrication. So for example, in this case, like you may have a, short circuit, right? So basically you want to make sure design is manufacturable with high yield. I mean, you can run very, very, very expensive simulations, okay? Lithography simulations, which are like based on physics, chemistry, photolithography, etching, and so on and so forth. But those are very, very CPU intensive. So what one of the key questions we would like to ask is like, hey, without going through those detailed lithography simulations, can you directly predict the lithography hotspot to avoid poor yield? Okay. So essentially, rather than like running this simulation, we can directly say, hey, with this, you are going to have some hotspot. Okay. So in that sense, it's a kind of classification problem. And actually, even more than 12, 13 years ago, we have published one of the first paper which used machine learning for lithography hotspot detection. So at that time, by the way, deep learning, it was not that hot yet, right? So we used the shallow learning, like a machine, like a support vector machine, right? But later on, of course, there are all kinds of deep neural network people have developed, and also even leading company Mental Graphics, which is now part of Siemens, has run a contest on this kind of hotspot detection problem. There are many, many papers which have been published on this. But I won't go into detail, but what I'm going to ask another question, which actually is a much harder question, which our work, LithoGAN is trying to address, is like, hey, without going through those litho simulations, can you even directly get the printed image? So remember, for the first question we asked, right? So it's a more classification, yes, hotspot, no, not hotspot, right? You give me any layout. But now I'm asking you, actually, what is really the final printed image, right? So how do we solve this problem? Right? It turns out that at that time, the GAN was also just recently introduced. So we used actually LithoGAN, which is an end-to-end lithography modeling using GAN, right? Generative adversarial networks. So the idea, again, is like you have certain inputs, right? We can get a bunch of snapshots, and which is related with your lithography kind of influence window. And based on that, instead of running detailed simulations to get the printed image of this feature that you are interested in, right? Now we actually, make it an image translation problem from this input to this basically output, which is a final printed image, right? So, we used GAN techniques to do that. Again, I won't go into details, but we found that, the GAN worked really well. And compared with the previous detailed simulations, physics-based, we can do thousands of times faster and still with acceptable errors, right? Like in this case, this is some input patterns. So you have a bunch of learning input and output, right? So you will then train your GAN models, and ultimately then you give us any this kind of input clip, and we can predict what kind of printed image this center feature looks like, right? So I mean, because lithography simulation is such a fundamental process, right? Because that depending on how lithography and manufacturability is, right? So then you actually will need to affect your design, because lithography heavily depends on who is its neighbor, right? Let's say during the placement, during the routing, right? Which cell is next to it, and so on and so forth, will play a pretty big deal. So if you found that, oh, you generate some lithography hotspot during your routing, then that's not good. Then we have to correct it, right? We have to maybe reroute, and we have to do some other operations. So that's why I call this lithography-aware physical design, and with lithography hotspot detection and then correction. For those of you who have lived in LA, probably you also know LAPD. So it also has a detection and a correction process. So of course, my contribution previously, my group has done a lot of work on this LAPD, right? Not this one. But anyway, my point that I'm trying to make is that this LithoGAN definitely opens a new direction, with tremendous potentials to bridge the back-end kind of manufacturing and physical design more closely. And also this kind of principle, detection, correction, right, can be applied to many other design and design automation problems, because in your design, oftentimes you also care about reliability, and you care about, for the future, there's a 3D IC and so on and so forth, right? So we also have done a lot of work here. And another thing that I like to talk about is like, in the, advanced process nowadays, right? The IC supply chain is pretty global. Maybe there's a little bit kind of anti-global trend. I mean, there's reverse, but still, there is still a big, like your manufacturing, design, and fabrication testing, they may all happen at different places, right? So how to ensure the security is very important. So to do that, actually, we have also done some work along this line to make sure what you design is secure and can be countering those IP reverse engineering and attacking and so on and so forth, right? So again, it's a big arm race problem between attack and the protection. So yeah. Anyway, I won't go into details, but that's also under the framework of learning for security, right? All right, so far I've spent most of my time on the AI for IC side. So next I will talk about IC for AI, which is actually very exciting to me and to close the loop. So as we all know, right? So nowadays, right, and all your modern chips, right? For example, your Apple iPhone or your other like Pixel phone or other modern processors, your Apple laptop or whatever, they all have neural processor units, right? To do AI acceleration, AI computing, right? But recently there was a lot of effort on this so-called photonic AI chips. Essentially, it's based on photonics and optics. Okay, so the first paper, one of the seminal paper, was published by MIT in 2017. So after that paper has been published, two startup companies will spin off from MIT on light matter and light intelligence. And then recently there are also quite a few other companies, trying to work on the AI and photonic chips. Okay, there are also some foundries that start to fabricate those photonic chips, and the EDA companies are also starting to provide some EDA tools on this. So what is the optical computing principles, right? So to do all this, right, you need to do some kind of optical computing. You can think about that, okay, I can use optical to do digital computing, but also can do analog computing. For the digital computing, you can think about, for micro ring, stuff like that, right? I have some input here. You can kind of use this to kind of generate some AND or 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 some other logic gates. Actually, we even tap out a chip and published in Nature Communications 2 years ago to do a arithmetic unit of optical computing. But I think another more interesting dimension to look at this is for analog computing using optical components. For example, MZI devices and you have light comes in, through these couplers and the phase. So you actually can implement some kind of, unitary matrix multiplication. And then also, if you have micro ring and micro disk, you have light comes in, you actually can do some scalar multiplication. And also for, optics, right? You could have wavelength division multiplexing, and then you can also do a kind of summation and so on and so forth, right? So, and the MIT paper actually was based on this analog computing paradigm. So the idea is like this, right? Think about it, right? So if you want to do matrix multiplication, so you can think about, okay, the middle part is some kind of MZI array, made by different device configurations. And then your light comes in as a vector. And once you go through this configured, MZI device kind of arrays, then the output is directly a matrix multiplication. Let's say Y is equals to W times X, right? So this is actually very interesting in the sense that it is directly using, the physics and optics to solve AI problems, right? I mean, to solve matrix multiplication, but matrix multiplication is a fundamental step, and it's in all the neural network engines. So it's very, very computational intensive. So by doing this, basically, you can provide, very fast and also very energy efficient, like a matrix multiplication. Right? But what's the problem? I mean, there are many, many different architectures involved for, optical neural networks or matrix multiplication. People have developed maybe spiking neural networks or like optical CNN and so on and so forth, right? But I mean, one thing I want to, this is a kind of busy slides, just shows the projection. There are different architectures involved. Some of these yellow colors is from my research group. And so the main problem of this optics is that typically optical device is very bulky. Of course, you probably heard about the free space optics. The lens is even very, very big, right? There's an integrated photonics people are now pushing, right? So kind of make it compatible with CMOS. But still, the optical device like MZI or micro disk, micro ring, they are still very, very big area-wise compared with the CMOS transistors, right? Think about it, right? For CMOS transistor, you are now talking about, 7 nanometer, 5 nanometer, right, process. But for those optical device, you are easily talking about the micron, right, or 10 micron. So you are talking about thousands of times bigger in terms of the dimension, right? So that's why you probably cannot afford to have so many kind of devices be integrated and in a photonic chip, right? And also, photonic device is sensitive to temperature and some other things, right? So we need to make sure. And when you're designing your optical neural network, you consider those. And then there's also a learnability issues, right? How you make your optical neural network to kind of be adjustable and to learn. And with this chip, you can do different things, right? Anyway, so there are a lot of like circuit architecture and algorithm co-design issues, which I will talk about. So this is some kind of stack that we have developed, right? Basically, from the software level, right? You have an architecture level. How do you do optical neural architecture design, and also how do you do model circuit and device co-optimization? And once you tap out the chip, then how do you deploy it, and also ensure you can do on-chip training, right? So along that line, by the way, right? So we have actually developed a lot of algorithms and tools. And including, we also open sourced this Torch ONN, right? So by the way, also my student Jia Qi has won last year's ACM student research competition grand final first place, right? So let me actually just show you a couple of case studies so that you can get some sense. So for example, in the original MIT paper, right? So their building block is MZI, right? And we found that actually you don't have to use MZI. You can use the direct this device like couplers, phase shifters, attenuators directly, and you can build some optical FFT and inverse optical FFT structures. And anyway, so basically they can also do matrix multiplication, but they have to do some special matrix multiplication, this is so-called circular matrix multiplication, and in Fourier domain. And anyway, I won't go into details, but basically what we show that by using our new architecture and algorithm, we can be actually 2 to 4x, kind of 3.7x area reduction, and so without like accuracy loss. So we actually even tap out the neural chips, optical neural chips, using this kind of architecture. And so as you can see, here is the chip, and we also have done the measurement and all this, right? So we found that it actually can get a really good compute density and energy efficiency. And yeah, this is a chip that ultimately we fabricated and bonded and packaged, right? So yeah, we also, students just won the Robert Hilbert Memorial Optical Design Competition Contest in July. Which is actually sponsored by Synopsys. So another case study I would like to mention is about on-chip learning, in the sense that you know, once you have the previous chip from MIT is only for the inference, right? But oftentimes, you know, you also want to, you know, really training takes a lot of effort, right? So how we can use that to do the training. So this paper, basically, we did a stochastic zeros order optimization and then use that to feedback and to do the training. Again, I won't go into details, but basically, by doing this, we also compared with some previous approach. We found a much better result. And one thing I would like to highlight why on-chip learning and training is important, right? Because, you know, your device, you know, like your optical device, they may also subject to thermal or some other variations, right? And if you have a pre-trained software, which then you know, map it to the circuit, and at that time your circuit may have, you know, temperature variations and so on and so forth. Then you will find that, sorry, you know, once you have a software trained model, maybe even with 97% or accuracy, but then once you map to the hardware, you will have actually 6-7% kind of, you know, reduction in terms of the you know, in accuracy, right? However, if you have you do a kind of direct training on chip, right? So you can consider those in situ like thermal variations directly, right? Because everything is done on hardware, so you know, so you are directly based on the, you know, hardware data immediately, right? So that's why, you know, on-chip training is very, very you know, effective. So we have also actually, I mean, the previous one that I showed is based on something called zeros order, right? Zeros order like optimization, stochastic zeros order optimization. We have also used developed a new method which was published in last year's NeurIPS by my student Jiaqi Gu. And so basically, we also developed an architecture which can do first-order gradient-based, you know, method. And by doing this first-order gradient-based method, the key message is that it can be much more scalable, and you can handle million parameters, you know, when you are doing the training. And so compared with the previous one, you know, we can only handle thousands of maybe MZI and so on and so forth. Right now, actually, we can handle huge, much bigger network. And also it is more efficient. And again, right, so because it is, you know, on-chip training, so any in situ like noise, you know, will be considered, right? So in that sense, we can build our optical neural network, which is noise resilient. Okay. All right, so yeah, I mean, we have actually a lot of work in the optical neural network, and also some even using optical neural network to help you design better device, and which I think if you are physics, you know, I think background here, right, you might be interested. We will be glad to talk with you more about those projects, right? But anyway, so because today time is a little bit limited, so let me just try to recap. So in this talk so far, basically, yeah, I talked about you know, AI for IC design. You know, I give you an example of DREAMPlace, which we can speed up placement by 40x, and then lithography modeling, and using GAN, we can actually speed up by 1,800 times. I didn't have time to show you the SRF or OPC, right? Basically, you know, you can directly generate those mask synthesis, and you can also get hundreds of times speed up. I also talk about the magical for the for analog IC layout, and also there's also security issues, right? So basically, AI can do a lot for everything from basically. I mean, here I showed this, right? If you are in the literature in the EDA community, right? So people have also tried to do AI for architecture, functional, and so on and so forth. And I have invited the co-author, the IEEE TCAD keynote paper on machine learning for EDA, right? If you are interested, I'll be more than happy to share with you. All right, so also to recap, in terms of IC for AI, right? So I have showed you how to build ultra-fast and light speed and ultra-efficient optical neural network accelerators, and with those photonic integrated circuits, right? By the way, those circuits are all integratable and compatible with the CMOS process, right? So in that sense, we can actually combine these with other CMOS chips, right? So become a part of the accelerator, dedicated accelerator for AI, right? And I showed you some FFT ONN and some other works, right? So anyway, so I think that kind of let me conclude my talk, right? So basically in this talk, I showed you how the advancement in AI, no matter whether it's software or hardware, or let's say software and algorithms, can help you to design those IC chips like DREAMPlace and so on and so forth, right? But meanwhile, right, if you have faster IC chips like photonic IC can do AI really energy efficient, really fast, and with all this enhanced AI capability, you can go back to help you design even faster chips, right? So I guess that's why we have this positive virtuous cycles. And remember I showed you that figure of Moore's law and also number of AI papers, right? So if we have both of these exponential work together with each other, I think it will be really, I think it can push the state of the art of each. And yeah. All right, so I'd like to, last but not least, thank my supporters and funding agencies, right? And of course, my students and postdocs who do the real work, and also my collaborators from different companies and so on and so forth. Right? Okay, with that, I will just conclude, and hopefully we can still have a few minutes for questions and answers. Right?
Good, good. So thanks, Dr. Pan, for the very nice talks. So is there any questions from the audience? Yeah, Dylan, go ahead. Yeah, so just unmute yourself.
Hi, yeah, thanks for the nice talk. I actually had a question. You mentioned that you have a version of DREAMPlace for FPGAs. Is this supposed to be integrated with like Catapult HLS or something like that? Is that, I assume it's sort of outside of the Xilinx Intel proprietary world.
I see. We actually, for DREAMPlace FPGA, we are integrating with VTR, which is from University of Toronto, right? So
okay.
this is still
Cool.
part of the placement engine, right? So the Catapult is more high-level synthesis. After high-level synthesis, you have RTL, right? And then you have to map it, and then you will do placement, right?
Okay, but I can't. I have to use sort of a non-proprietary Xilinx or Intel setup in order to use this. Is that right?
Actually, no. You have a great question. No, actually, there is something called Open FPGA. People are also using Yosys,
okay.
That kind of yeah. There's also framework that can do non-proprietary.
Right. Yeah, exactly. This was my question. Okay. Okay. Yeah. Thanks.
Okay, you're very welcome. Thanks, Dylan, for your great question.
Any other questions?
Yeah. Okay.
Yeah.
I have a question.
Oh, hi, Demi. Hi.
Hey, David, great talk. Very impressive. Right. So for the photonics, I have heard a lot of interesting trend. So from a commercial point of view, do you know what's the current scale, right? So how many devices, what's the scalability, and what's the most useful applications?
Okay, yeah, this is a great question, right? And so I know that some company light matter, right? I think they have shown some big chip at hot chip, right? If you go to a conference called hot chip, right? But they are still based on more MZI device because this company is funded by some of the co-authors of this MIT paper, right? So, but in terms of deployment, right? So they also have other, CMOS based, right? And then they have a big accelerator. I think how many devices? I didn't quite follow that. I think, of course, because of the constraints, right? You cannot have very, very, very big like CMOS, right? I think they, but if they have something dedicated for autonomous driving or for some data centers, right? They can fabricate some pretty big chip, which then they can scale. I would say, I haven't done the computation, right? If not millions, but hundreds or thousands, right? So those they can do series pretty big, like multiplier, right?
I see. So, but
then they can reuse. They can reuse those. The things that they are very fast, so they can reuse those. You need to reuse those, right?
Right. So so for example, for CMOS, of course, the fundamental limitation for scalability is Moore's law, right? So this photography and all that. And for this one, what's the fundamental limit?
Okay. The fundamental ones on one hand, right? People are inventing new device. I think there are a lot of many physics people here at photonics. So to really scale the feature to be smaller, but I think there is some fundamental limit in optics too, right? Maybe 1 micron or maybe hundreds of nanometers. I mean, there is some limit, right? You cannot go. However, for optics, you can also do another scaling. It's called a wavelength division multiplexing. So basically, each waveguide you can, optical is very interesting compared with the electrical. And when you have electrical, if you have 2 wires that are short, then it's short, right? You cannot have 2 wires cross each other, and 1 wire can only transmit 1 signal. But for optical, you can have 1 optical waveguide to transmit 64 signals, something like that, with 64 different wavelengths. So in that sense, you can kind of scale in that kind of number of wavelengths, right?
Right. That's only for communication, right? So is that right?
Yeah. Oh, yeah, it is communication. But meanwhile, okay, when you are doing, we haven't shown. So we actually, I didn't show the details here. But when you do multiple, you can actually have multiple wavelengths here that can accumulate and then, do the, to do kind of more operations, right?
Okay.
Using 1 device and 1 waveguide. Right?
Got it.
1 waveguide, but with different wavelengths.
Yeah. Okay. Yeah. Thanks.
Yeah, that kind of thing is the scalability, right? So number of waveguides. And another thing you could scale is like for those devices, we even tap out some prototype, right? So for example, I don't have the slides here, right? But basically, if you have a micro ring, typically 1 micro ring maybe have 1 control, right? You could actually even have multiple control, and we call it a multi-operand, right? So then you actually also can scale in another way.
Yeah, that's very interesting.
Yeah.
Yeah.
You have to play with some device physics.
Right. Yeah.
I'm not really an expert there, but my collaborator, they have actually demonstrated in the fab, right? So.
Got it. Yeah. Okay. Thanks.
Cool.
Yeah, very good question. Thanks, Demi. Right.
Yeah. So I guess right now is we passed the 4 p.m. So we are like let's say so it's a time for this seminar. So I was wondering, so maybe if you have like further questions, so you can maybe I'm not sure, like David, do you still have more time, like maybe 5 more minutes or no? Or you need to go?
I have an office hour right now.
Ah,
I have
I
an
see.
exam for students, right? But they haven't knocked on my door yet, right? Anytime they knock on my door, I may have to answer that, right? But
Yeah. So because it's time for close our meeting, but indeed I have a few questions regarding the AI for IC part. Yeah, so I'm wondering whether I can ask those questions or
sure,
not.
you can ask.
Yeah, so I was wondering for the like a placement that kind of like a combinatorial problem. So are you using let's say do you think we need to consider some like the objective function we want to have is more like a white box or more like a black box? I mean, for example, if I want to predict the latency or predict maybe it's I think the current maybe the wear length is just theoretically designed, but not like something some ground truth stuff, right? So I'm not sure whether I make
wireless is a ground truth, right? Wireless, because in general, smaller wireless is always good for chip design, you know, because you have small, easy to route, and you have smaller wireless, meaning, you know, better delay, right? Less delay.
Yeah.
So that one is actually it's not just a combinatorial optimization. We make it a continuous optimization, right?
So you need to relax that a little bit, right?
Relax the XY location to be continuous, right? Because, you know, otherwise, right? Ultimately, when you do legalization, that cannot be on top of each other. But before that, you make them to be continuous, right? So
I see.
But some stuff, right? You know, people are used for during the chip design. If you want to predict the timing and other stuff, some of them, or especially like hotspot, right? And then, you know, some of this may not be totally continuous, right? But yeah.
I see. So, so my question is, for example, if we want to predict the time latency or something, is there like a direct mapping from your placement like to the time latency, or if not, like what's the current solution for that? Some other.
When you have a placement, right? So indeed, right, there are some well-established literature. You can do something called a static timing analysis, right? Based on analysis, it's how do I explain? Based on certain analysis, you can get because, you know, okay, the graph is very complicated. You know, so you have some cell are so-called flip-flop. It's like those are the sequential elements. You know, that's a timing starting point and timing end points. Then you may have branches, and you may, you know, have this, and depending on that. So it's it's a very, very complicated graph, and based on that, you can actually get timing, right? Looks like some students are coming to my office.
So thank you for so much. So if I have more questions, maybe I can follow up with some emails too. Thank you so much. Okay. So great. Thank you for the talk. And I think it's very nice for us to have you here to have this nice talk. Maybe we can close our today's meeting. Close today's seminar. Thank you, everyone.
Thanks very much.